The HEIR Compiler. The talk is given by Jeremy Kuhn from Google. Welcome.
Hello, thanks everyone. This is the clicker, yes, okay. I'm going to be talking about the HEIR or HEIR Compiler and how to write optimization passes in it. There's a lot of content, but before I get started, I wanted to say that it was exactly a year ago today that I first floated the idea to the FHE community of having a unified compiler that handles everything. And while we're still very far away from achieving that, I've been very, very proud of the community for the positive support and spirit of collaboration. I spent this week at the Hacks workshop, and I got a taste of the zero-knowledge proofs tooling ecosystem, and it is very competitive and very fractured. And so I'm, by contrast, working with the FHE folks has just been so delightful. Thank you. Okay, so quick agenda. I wanted to give a pitch of the HEIR project for people who haven't heard of it before. Then I'm going to give a quick overview of MLIR, which is the library that we're building all of this on top of. And then I'm going to dive into the nitty-gritty of like what it looks like to actually write some optimizations. And then I'll give some resources for further reading at the end. So the pitch, okay, one slide. We are building a compiler toolchain for fully homomorphic encryption that includes all of the established ideas. So all the schemes, all of the optimizations that are known to become a FHE research platform, accelerate FHE research, and lower the barrier to production FHE. The focus for this year is on hardware acceleration. So all of these folks who are building these lovely hardware accelerators, by the time they are ready, we want to have the compiler ready to export programs to them so we can get benchmarks across schemes, across hardware, across different optimization tricks. It's going to be great. That's our focus. And if you're interested in joining in, we have a working group. That QR code takes you to a calendar, but you can also just go to heir.dev. We have a meeting every 2 weeks. The next one is April 4th. So I'll let people take a picture. And then there's a list of some of the projects that we're focusing on right now. Okay, so quick overview of MLIR. There are a few acronyms here going on. So MLIR stands for Multi-Level Intermediate Representation. What does that mean? It means it's a compiler toolchain, a library for building compilers. HEIR, by analogy, is Homomorphic Encryption Intermediate Representation. That is the custom stuff that we have extended in MLIR to represent concepts from FHE. I will give a few examples in this talk, but there are quite a lot. The main thing that you get out of MLIR, or the first thing that you get, is a textual representation of what your program looks like. It is strongly typed. It is a static single assignment form for compiler folks who know what that means. You get all of these built-in operations from the upstream MLIR project, including arithmetic, I'll show some example here, including function calls, including arithmetic, including tensors, including for loops of different flavors. And so you don't need to understand all of the stuff that's happening in this slide. I see. I made some last-minute changes that did not make it into this slide, but so we'll go with this. So this is a Hamming distance or distance function that subtracts two vectors and squares them and sums up the result to get a distance. But the point that I want you to take away from this slide is that all of the different operations that you have in MLIR are grouped into namespaces called dialects. All of the dialects that you define, including your custom ones, can coexist. And the point of these dialects, aside from structural things like functions and control flow, the point of the dialects is that you represent your program at different levels of abstraction that are appropriate for particular types of optimizations that make sense at that level of abstraction and are easy to do in that context. Okay, so the FHE stuff that we'll be doing for the rest of this talk is in the BGV CKKS style of arithmetic FHE, and we're going to be focusing on reproducing some of the optimization tricks from the HEIR Compiler. So the idea, one of the main ideas there is that when you're doing SIMD operations and you have this rotation operation, you want to sort of pre-align all of your things so you don't have to do very many rotates, and you can do things like linear size reduction to a log number of rotations and additions, right? Yes, okay. And part of the goal is to reuse as much of the upstream MLIR stuff as possible so we don't need to write compiler stuff ourselves. So there are two ingredients that I'm going to show that are like custom extensions in HEIR of MLIR. So the first thing is a dialect that we made called the tensor extensions dialect. This is the thing that includes all of the operations that we have on batched ciphertext that does not make sense to have in upstream MLIR because they're normal CPU models don't have these restrictions. So we have an operation in this dialect called rotate. It cyclically rotates a vector by a statically known shift. And what do I want you to get out of this? So this DSL that you're looking at here is something called TableGen. So this is a domain-specific language, part of MLIR for defining the syntax and some of the semantics of your operations and your types. This is only a slightly abbreviated version of what's actually upstream. The upstream stuff has some extra documentation that gets auto-generated into the website. I won't go into that too much. But the main thing here is that you can define the inputs to the function, the outputs to the function, and how you would like it to be printed and parsed in the textual representation. Once you hook this thing into your main binary, then you can write your operations in MLIR just like any other MLIR code. So it's very quick to define new types, new operations, and new dialects. The second thing is what we call the secret dialect. So this is a bit more complicated example of a dialect, but it defines a new type that is a scheme-agnostic abstraction of this piece of data is private and should not be known to the server. So we call that the secret type. It wraps any type you want. So you can say this I32 is secret. You can say this tensor of two-dimensional tensor of I16s is secret. There's no restrictions there. And then we have what we call a generic op. So this might not be the best name, but the idea is that you can take any plain text computation in MLIR, and then you can wrap it in this operation that lifts it to operate on secrets. So the benefit of doing this is that the body of the secret generic op can get the benefit of all of the upstream optimizations. You don't have to write your own ops for adding FHE ciphertext because you can use the upstream ops and wrap it in a secret generic. Okay. This is going very fast. I hope everyone's still, okay, great. Excellent. Okay, so here is an example of how you would use some of these passes. There's one up there called insert rotate. That will be the focus, but I'm just going to show you what the lowering passes look like and the optimization passes. So we start from this Hamming distance function that it actually has some inefficiencies in it. You will see it is computing the same subtraction twice that it doesn't need to do. But the point is that you start by just saying, okay, this is the input to my function that is secret. You'll notice the bold part at the top says what's secret. And then there are some entry passes that say, okay, from the annotation of what's secret, I'm just going to propagate that secret information through the program and start wrapping things up in secret generic so that I can separate the plain text parts of the computation from the secret parts of the computation. And then there is a canonicalized pass which does some very simple things like, so in the secret dialect, we have canonicalization, which takes stuff that's plain text inside of a secret generic op, pulls it out, does other simple things like if there's a secret generic that has no secret arguments to it and no secret stuff happening, just deletes it entirely. So this is some sort of like structural stuff. Then there's an example of, a simple loop unrolling op, which is not necessarily what you always want to do, but in this is just a nice example. So we'll take that op, we'll unroll the whole loop. It's not a very big loop, but it turns it into a whole bunch of scalar operations. You extract from the tensor, you do your operation, you aggregate it with the sum, and then you get this IR that looks like this. Notably here, there's a constant, the CSE stands for constant sub-expression elimination. This was an optimization that I did not have to write because it is in MLIR and it applies to all MLIR for free. So you can just use it and you don't have to write your own special thing in your own custom compiler. Okay, so now we get to the insert rotate pass. This is the interesting thing that encapsulates some of the HEIR optimizations for BGV. So here we are looking at the scalar operations that extract something from a tensor. We're saying, okay, that's expensive in FHE, so we're going to turn that into just an addition of the entire vector. And then we're going to look at when things need to be aligned a certain way, we'll insert rotate ops to align them properly. And then at the end, at the very, very end, we can extract, the particular the particular index that is the data item we're looking for. And you'll notice that there's a loop, an unrolled loop on the left-hand side, but on the right-hand side, there's no loop anymore. It has smartly batched everything into, just a couple of two rotations for the loop of size 4. So, okay, that's log. And then there's no longer any extraction operations. Okay, so yeah, there's a lot happening inside this pass. I'm going to give a flavor of what's happening in there and how we represent those optimizations in HEIR. And but before I get there, this is obviously not the whole story. There are a whole bunch of other passes and lowerings that eventually get you to something that is actually FHE that you can run. I'm not going to cover those, and they're at various states of completeness and workingness. So in this one, you might continue by saying, okay, now I'm going to pick a scheme. I'm going to lower it to BGV, do some BGV-specific optimizations, and then maybe you can decide to emit OpenFHE code or go straight to LLVM if you'd like. So these are all things that we are actively working on or already work. Okay, so declarative rewrite rules. Okay, so we are back in the land of TableGen. So TableGen is also a domain-specific language for defining your local optimization patterns that you would like to apply. So the two examples I'm giving on this slide are for canonicalization patterns. So these are the things that get wrapped up in the -- canonicalize flag, and they do very, very simple things like if you're rotating by 0, you don't actually need to do anything. You can delete that up entirely. And if you have 2 sequential rotations, then you can just combine that into a single rotation by the sum of the shifts. And so the syntax here is that this pat is short for pattern, and it takes 3 arguments. The first thing is sort of a match on the IR that this MLIR will then go search for expressions that look like that and figure out, okay, which things could potentially be replaceable. The second item is the thing that you would like to do once you've found that match. And the third item in the list is a set of constraints that you can apply to say this is when that replacement should actually be applied to the match. So the first one is quite simple. If you see a rotate op and the argument is 0, you can just replace it with the tensor itself. The second one actually inserts a new addition operation and then says instead of doing 2 rotates, you just do 1 rotate. Some more complicated examples. So TableGen has things like loops, so you can loop over the operations you would like to apply your pattern to if you have some sort of templated pattern that makes sense in that context. So in this one, we have a pattern where if you apply a vectorized arithmetic operation to 2 tensors that have been rotated by the same amount, you don't actually need to do that. You can apply the arithmetic operation first and rotate later, so you've reduced from 2 rotations to 1. And the point is that when you do this, you are, as an output of one application of this pattern, you might have 2 rotates that are now, they weren't next to each other before, but now they're next to each other. So the previous pattern on the previous page would apply, and you put all these patterns into what they call the greedy rewrite engine, and it will just look for opportunities to apply the patterns until it reaches a fixed point. And there's a lot of benefit you can do to just naively applying a bunch of these local patterns. Okay. Yes. All right. Here's a more complex pattern that gets into the heart of what the insert rotate pass is doing. So here you can see there is like a tree of binary operations, and there are 3 rotations happening there. And basically, if you have 3 rotations, you can take the first 2 and pre-align them to the second one, or to the third rotation, so that you don't need to do the third rotation at all. So this is maybe a bit too much detail, but this is an example of a pattern that we added. And then this shows like, okay, we have this DSL. How do you actually get the DSL into the compiler? Well, in TableGen, you can specify a pass, right? And then that generates a whole bunch of C++ boilerplate. And then all you have to do is implement this run on operation function. And in this case, we are also pulling in auto-generated C++ for all those patterns. We have this thing called a rewrite pattern set. You throw all the patterns into that, and then you say, I would like to apply these patterns greedily across the whole program or across whatever subset of the program this pass is attached to. And so this gives you a sense of, there's some extra boilerplate, but it's very easy to get things into the compiler. Okay. Now, I want to talk about, how am I doing on time? This is halfway. Am I halfway through my time? Yes, okay, perfect. 10 minutes, okay. Okay, I can do 10 minutes. Okay, so local rewrite, these rewrite patterns I was talking about are very localized constructions. They're more sophisticated things you'd like to do are global program analyses. So I'm going to give you 2 examples. And in still staying in the context of these HEIR slot alignment things, what if the slot we would like to align our rotation to is like far away in the IR? It's not something that is locally right next to the op. Well, you have 2 options. The first thing is you can write whatever C++ you want, right? You can do anything you want, or you can use the one of the many classical compiler techniques in data flow analysis. So there's this concept of an analysis pass, which is just going through your program and pre-computing some information that you can then access later when you're actually doing optimizations. And the most common kind of thing for this is what's called a data flow analysis. A very quick example of a data flow analysis in classical compilers is you would like to know what static values you can tell about your program based on where you are. In classical compiler world, branches are the enemy. So when the branches combine, you have to decide, okay, if it says x is 44 and x is 5, how do I turn that into information when the 2 branches collide? The structure for doing this is called a join semi-lattice. So this is basically you say, okay, what's the join operation in this lattice, and at what point do I sort of give up at the top, and at what point do I start at the bottom? If you define this in MLIR, the rest of the framework is handled for you. It will do the process of propagating all of this information through. You just have to say, here's my lattice, and then here's what to do when it says x equals 5, how to sort of instantiate the bottom of that lattice. So here, okay, this is too small, but here's what it looks like in the C++. On the left-hand side, we have the target slot data structure, and all you have to do is define this join operation that decides what to do in the lattice. On the right-hand side, you can see an example of if you're inserting a scalar into a vector, right, then that's the point at which you say, aha, that's my target slot, so this is the instantiation, the bottom of the lattice. And then on the left-hand side, this is just us saying, hey, HEIR Compiler framework, I'd like to do a data flow analysis. I'd like to start from the end and go backwards, and here is my lattice data structure. So this is, okay, too small for the screen, but there's a link to a pull request that has it in gory detail. Okay, and then using the data flow analysis, you might say, I love writing these simple rewrite patterns. I don't want to have to write C++ for everything. Well, it's nice. There is, with a little bit of boilerplate, you can basically attach the information from the data flow analysis to the SSA values in the program and then access them in your rewrite patterns. So this is sort of the final, like, how do you convert a scalar operation to a tensor operation and do the alignment at the same time? Well, you say I have an arithmetic operation. I'm seeing what does that need to be aligned to? What's the target slot for that? Then instead of extracting at a particular index, I'm going to rotate so that it's pre-aligned with that target slot. There's this get target slot attribute helper function that extracts that information. And then I just do my replacement sort of as normal. Okay, whew, great. So I talked a lot about BGV. The BGV stuff, the sort of SIMD style optimizations, those are relatively new. Most of what we've been working on is making our old Google transpiler obsolete. And that means supporting a lot of circuit optimization for TFHE style computations. That is also in there, and that's me just trying to say you can do whatever you want in an optimization pass. We build a hardware circuit, we pass it to a hardware circuit optimizer, we take the result and we build MLIR that does truth tables and AND gates and XOR gates and all that stuff. And you can do that too if you want to, but I'm not going to talk any more about that for now. Okay, that was a whirlwind. I was a camp counselor when I was in high school, so I have that energy. You might not. I have part of my job here, I see, is bringing all of the compiler information from the compiler community, condensing it in a way that the FHE community can understand. And as part of this, I've written a whole bunch of articles that are MLIR from scratch for people who know C++, but nothing else about compilers. Okay, so it starts from the beginning, just how do you run passes, and then it goes all the way down to, so in the last article, I implemented the linear programming optimization of Pallier et al. On like how do you do opportunistic bootstrap insertion, right? You have a noise model, like an LWE-like noise model, and you want to insert bootstraps to minimize the total number of bootstraps. So that's the last article. So it's like a very nice progression towards doing something useful. And then if you're looking at HEIR and you're confused, Well, all of the stuff is in there in a simpler format, so you can like use that as a bootstrap. Yes, okay. A way to learn about what's actually happening in HEIR. Okay, that's what I got. Come join us. Yes, thank you. Questions?
Thank you very much.
Thank you for the talk. What front ends are you support, or do you currently support? For
Good
this?
question. Yes. So we have varying degrees of support for C++, for TensorFlow graphs, and I'm slowly working on Python as a front end. But the longer answer to that is that all of these are slightly broken in small ways, and I need to go fix the upstream projects that we're depending on to make them work better for us.
So what's the lowering pathway from MLIR down to hardware accelerator ICEs? Because that's our intention, is to use MLIR to drive our accelerators. And I want to actually make that the case for the entire DARPA DPRIVE program phase 3 benchmark. So tell me about that.
Absolutely. So our immediate path towards that is export to all of the libraries that the hardware accelerator developers are currently using as their starting point. So we export to OpenFHE and we export to TFHE Rust. If anyone else has a hardware accelerator that needs different support, come to us and let us know. The long-term story is that we would like to implement all of the cryptographic lowerings from scheme operations to polynomial math primitives in the compiler. We have a polynomial dialect that handles sort of the basic structure of this, but we haven't implemented very many of the lowerings yet, or any of the lowerings yet, I think. But in the long term, we're expecting hardware accelerator designers to have their chips be essentially polynomial number crunching machines, and we would like to do the scheduling at that level.
So on the TFHE, you use the Yosis, which I think is like a synopsis type plugged version, yeah? Which is very binary circuit based. Whereas TFHE, if you use it properly, is all LUT based, which is more like an FPGA toolchain. So have you looked at that as well? So
Yosis has LUT optimizations up to 6 bits. We have found that TFHE Rust works best at 3 to 4 bits for the lookup tables. But some of the things that is not in the compiler right now is all of the magic happening in concrete. Things like the special lowerings of particular machine learning operations. That's something we aspire to do but haven't had time to do yet. Yes, then the security analysis of CGGI is another thing that we have not tackled yet.
So this is more of a comment than a question. So when you were talking about lattices, that has nothing to do with lattice.
Nothing to do with FHE lattice security. No. Yeah, that's why I said semi-lattice. It's an algebraic data structure.
Oh, thanks.
Okay, and last question.
Thanks for the talk. This is really cool. I don't know anything about this, but it's cool, and you showed that very well. I'm curious what Google's support for this is like. Are you pushing for internal applications right now? Is this something you want to do for the community? What's the direction?
Yes, I gave a talk at one of the FHE.org meetups where I wax poetic about why we're doing this. But the short story is that Google is thinking of this as a long-term investment in one of many tools in the private computing toolkit. That we are certainly not yet the moneymaker in this sphere, but we are, planning to be around for at least a couple more years. We are riding the coattails of other successful privacy applications at Google right now. Yeah.
Thank you very much, and thanks again, the speaker.
Thank you.